Welcome. In this section of the video, we shall dive into one of the most interesting and fundamental concepts in fluid mechanics, the boundary layers and flow separation around a sphere. Understanding these concepts are essential for anyone working with aerodynamics, fluid dynamics, or engineering design, as they have significant implications for drag, energy dissipation, and behavior of object moving through fluids. So, let's start by considering a simple scenario: a sphere moving through a fluid. As this happens, the viscosity of the fluid causes it to stick to the surface of the sphere, creating a special region called as the boundary layer. This is a thin, often invisible layer of fluid that forms along the surface of the sphere. The boundary layer's behavior is crucial because it determines how the fluid flows around the sphere and whether the flow remains smooth or separate. When the flow separates from the sphere's surface, it leads to the formation of a wake behind the sphere. This wake plays a significant role in increasing drag and energy dissipation, making the flow around the sphere more chaotic and less efficient. In this video, we are going to cover the following key points: how boundary layers form and evolve as the fluid flows along the surface of the sphere, the role of pressure gradients and how they lead to flow separation, the impact of separation on the wake structure and how it influences drag and overall flow efficiency. Now that we have a basic understanding of why boundary layers matter, let's explore how they form and behave in more detail. The fundamental reason boundary layers form is due to viscosity. As the sphere moves through the fluid near its surface experiences friction. This causes the fluid particles to slow down compared to those farther away from the sphere. The no slip condition, which means that at the surface of the sphere, the fluid velocity is zero. The fluid particles that are right next to the sphere must adhere to the surface. As we move away from the surface, the fluid velocity increases, eventually matching the velocity of the free stream flow, which is the flow far from the sphere. This difference in velocity between the surface and the rest of the fluid creates a velocity gradient. This is the foundation of the boundary layer. It's a smooth transition of the fluid velocities from zero at the sphere surface to the free stream velocity in the surrounding fluid. As the fluid moves over the surface of the sphere, the boundary layer grows in thickness. It starts at the front stagnant point, the very first point where the fluid makes contact with the sphere. From there, it begins to grow as the fluid flows downstream. As the flow moves toward the equator of the sphere, the boundary layer becomes thinner. However, this is also where the flow velocity is highest, and there are more shear forces which can cause the boundary layer to become thinner or more turbulent in some cases. Beyond the equator, the boundary layer continues to grow as it moves towards the rear of the sphere. At low velocities, the flow in the boundary layer is laminar. This means the fluid layers slide smoothly over each other without significant mixing or disturbance. This results in a relative thin boundary layer. As the velocity increases and the Reynolds number becomes large, the boundary layer becomes less stable. Eventually, it can transition into a turbulent boundary layer characterized by chaotic flow and increasing mixing. This causes the boundary layer to be thinner and become more complex. Now, you might be wondering what happens when the flow separates from the sphere? How does that affect the energy of the system? The answer lies in energy dissipation. When the boundary layer separates from the surface of the sphere, it creates a region of disturbed and chaotic flow, forming a wake behind the sphere. These regions of turbulence increase the amount of energy lost in the form of heat and chaotic motion. For spheres moving at high speeds or with high Reynolds number, the wake becomes more turbulent, leading to greater energy losses. This explains why objects moving at high velocities through fluids require significantly more energy to maintain their speed. Let's take a moment to summarize what we have learned so far. A thin layer of fluid forms close to the surface as a result of viscosity. This layer grows thicker as the fluid moves downstream along the sphere. After the sphere's equator, the pressure gradient changes and the fluid is pushed away from the surface, causing the flow to separate. This leads to the formation of a turbulent wake behind the sphere. The wake is the disturbed region of fluid that forms behind the sphere. At low speeds, the wake remains steady and well behaved. However, at higher speeds, the wake becomes unsteady and turbulent. As speed increases, drag increases as well. At low speeds, drag is primarily due to viscous effects and friction. At higher speeds, drag becomes dominated by the pressure difference between the front and rear of the sphere, as well as the turbulent wake. Understanding this dynamics is crucial in many applications. For example, in aerodynamics, the design of golf ball and aircraft often considers how boundary layers and separation affect drag and performance. It also has importance in environment modeling such as sediment transportation, while understanding how water flows around object can influence how particles settles or move. To wrap up, the study of boundary layers and flow separation is not just academic, it has real world applications in everything from vehicle design to climate modeling. Now, let's start understanding the flow of fluid past the sphere is a cornerstone of fluid dynamics with applications that stretch across various scientific and engineering fields. The way fluid behaves around spherical objects is influenced by several factors, including the Reynolds number, which characterizes the flow regime, whether it's laminar or turbulent, and the drag forces, which determine the energy required to move an object through the fluid. Let's begin with how flow past the sphere applies in environmental systems. This system often involves natural or engineered processes where particle interacts with fluid. Understanding this flow can help us design better systems for controlling pollution, understanding atmospheric processes, and more. Sedimentation is a process where particles such as sand, pollutant, or minerals settle out of a fluid under the influence of gravity. The speed at which these particles fall is governed by Stokes' law, which is used to calculate the settling velocity of a small spherical particle. Stokes' law tells us that the velocity at which a particle settles is directly proportional to the square of its radius and the difference in density between the particle and the fluid. This is crucial in sedimentation tank used in water treatment plants, where particles settle at the bottom while cleaner water is allowed to flow out. By understanding this flow behavior, engineers can design more efficient systems for purifying water and managing waste. In atmospheric science, aerosols such as cloud droplets, dust particles, and pollutants behave like small spheres moving through air. Understanding how this particle interact with surrounding air is key to many environmental studies. For example, cloud droplets grow by colliding with other droplets. This is a process heavily influenced by their settling velocities and flow interactions. The dynamics of these interactions, which are governed by drag forces and Reynolds number, help meteorologists predict rainfall patterns. By studying the motion of aerosols and their interactions with other particles in the atmosphere, scientists can better model weather systems and air quality. Now let's shift our focus to industrial processes. In these applications, the interaction between spherical particles and flow fluid is critical to optimizing efficiency and designing better systems for manufacturing and chemical reactions. One industrial application where flow past spherical particles is crucial is in fluidized bed. These are used in chemical reactors and combustion systems, where a bed of particles is suspended by an upward flow of gas or liquid. In these systems, spherical particles interact with the fluid, and the drag force acting on each particle determines whether the particle remains stationary or becomes suspended. The efficiency of fluidized beds rely heavily on understanding the drag forces and flow behavior around these particles. For example, in catalytic reactor, fluidized beds are used to enhance the contact between the fluid and particles, which speeds up reaction and improves process efficiency. Filtration systems are another industrial application where the behavior of spherical particles plays a significant role. Whether it's air filtration or water filtration, the ability of a filter to capture particle depends on understanding how spherical particles move through fluids. For example, in air filtration systems, particles like pollen or dust are captured by fibrous filters. The filter's design takes into account the drag forces acting on the particle, ensuring that smaller particles are effectively trapped. Engineers rely on the principle of fluid dynamics and flow past spherical particle to optimize filtration system for efficiency and longevity. Finally, let's look at some biomedical innovations where understanding the flow of fluid past spherical particles has a direct impact on improving medical treatments and technologies. In drug delivery systems, nanoparticles are often designed as spears to transport medication through the bloodstream to target tissue. At small scale of nanoparticles, viscous forces dominate the flow behavior, making Stokes' law essential for predicting their motion. By optimizing the size and surface properties of these nanoparticles, engineers can ensure efficient drug delivery while minimizing drag forces that might slow down their movement. For example, nanoparticles can be engineered to navigate through the bloodstream, passing by natural barriers and delivering drug directly to cancerous cells, improving treatment efficiency. Another exciting biomedical application is the lab on a chip technology, which allows for the manipulation of small amount of fluid for medical testing and chemical analysis. In these devices, spherical shells or beads are often used as carrier to move fluid or sample through microchannels. At the microscale, the Reynolds number is extremely low, meaning viscous forces dominate. Engineers use these principles of flow past spherical particles to bend microchannels that precisely control the movement of fluids and particles. This is essential for tasks like cell sorting or mixing. In diagnostic tests, by understanding how spheres behave in microfluidic environments, designers can create more effective and efficient lab-on-a-chip devices. In conclusion, the study of flow past a sphere provides invaluable insights into the fundamental dynamics of fluid motion. From drag forces and boundary layers to wave formation and turbulence, these concepts are key to understanding fluid behavior across a wide range of applications. The Reynolds number is central to predicting how flow behavior from laminar to turbulent regime. However, challenges like predicting turbulence, transitions, and modeling multi-particle interaction remain active areas of research. Emerging tools like DNS simulations and machine learning are helping us tackle these challenges, offering exciting new possibilities for improving our understanding of complex flows. As we continue to develop these tools and models, the future of fluid dynamics holds great promise. From optimizing industrial processes to improvising biomedical technologies. Thank you for joining us on this journey into the fascinating world of fluid mechanics.